Welcome to an NMR tutorial on less common phenomena, or if you prefer, weird stuff. So this is a collection of standalone topics which will not come with a great deal of detailed background, but are just here so that you're aware of them if you happen to come across them in your work. So the first of these phenomena that I'd like to address is something called the heavy atom effect, and this is where heavier elements modulate chemical shifts of attached nuclei. Now, some elements of this remain in the area of active theoretical research. It's pretty complicated, but what is usually relevant for us is that when you have one of the heavier halogens, such as a bromine or especially an iodine, attached to an atom, usually a carbon, then you should expect a big upfield shift. And this is especially true if it is attached to an sp2 center. I should mention there is an analogous effect on protons. It's smaller and it's orientation dependent, and it's just usually less visible and relevant. And I'm not going to go into any detail on that. Now, if we look here at some ethane analogues, where we started with ethane at the top and then we have successively replaced one of the hydrogen with the 4 different halogens, and then look at the carbon shift of the attached carbon in the red box. Let's see here. In fluoroethane, we have a huge shift for the attached carbon. This is really not surprising. After all, fluorine is the most electronegative of the elements. And we do also have a smaller shift in the other carbon signal. Now, if we move on to chlorine, chlorine is a lot less electronegative than fluorine, but still considerably more electronegative than proton ethane. And this results in a signal that's at about 40 ppm. We then go on further to bromine. Again, it's less electronegative than chlorine, but more so than hydrogen. And we drop to another 10 ppm, we're at about 30. Now, for iodine, we would expect this trend to continue. Again, iodine is less electronegative than bromine is, but more than hydrogen. So we'd maybe expect a peak around here. However, as a result of the heavy atom effect, we see this peak for the attached iodine all the way down here at around about 0. So if we now look at halobenzenes, these are sp2, so these are, we expect to see a stronger effect. Again, we can see a single peak for benzene, it's about 130. If I just highlight the ipso attached carbon, and again for fluorobenzene, we're seeing the ipso carbon is heavily influenced by the attached fluorine. It's all the way down at about 160 ppm. And again, the effect of chlorine is relatively smaller, but it's still more electronegative than the hydrogen would otherwise be attached, and so you see it downfield shifted. By the time you get to a bromine, however, we should see the same trend as previously. So the shift should be smaller than it is in the chlorobenzene example relative to benzene, but it should still be down. However, we can see it is now forgive my terrible drawing, but upfield of the benzene signal. And if we then take this example further to iodine, now the difference is much bigger, and the heavy atom effect has shifted our carbon all the way down to around about 95 ppm, just on the edge of what we would normally consider the aromatic region. And this is quite distinctive. You can tell what carbon on that ring system that signal corresponds to, and you can combine this with 2D methods like HMBC and use it as a starting point in structural assignments. So now I want to talk about the effects of pi system overlaps. So here are a couple of simulations of benzene rings, and in these the ring current on the outside runs in alignment with the magnetic field, and on the inside it is in the opposite orientation. Now, we know these systems affect protons and indeed the carbons in the ring, which are de-shielded usually, and this is by the ring current in line with the magnetic field. These systems can actually affect other protons that are close enough in space, and because their exact relationship with the ring is more variable than that of the protons and carbons attached, the nature of this is orientation dependent. I'll take you back to an example that we had in an earlier tutorial that I promised to explain. So the curious feature was that these protons are all the way up at 9.5 and 9.6 ppm, which is an unusually high shift for a pair of aromatic protons. And although it's much less obvious from the shift, this signal is actually also anomalous, and they're caused by the same phenomena. So they come from this molecule. Perhaps the shift is less surprising when you see this. It's a cationic double nitrated heterocycle. So you would expect the shifts to be fairly downfield. What I want to draw your attention to, however, is that you would expect the most electron poor positions to be the ortho nitro group, which would be here. And in fact, those signals are here. You can see those are doublets of doublets. Now in reality, these signals, which are the ones at the back of the ring system, are significantly downfield, despite not being in the more activated position with regard to the nitro group. So, despite being in the meta position where they're not conjugated with the nitro group. So what's the explanation for this? Well, it's caused by pi system overlap. Each of these protons is experiencing some of the adjacent pi system from the rest of this ring system. And that is what is reinforcing the shielding effect of the aromatic system, and they are pushed downfield to these very high chemical shifts. Now, I said this proton is also anomalous, and I think that's more obvious when you look at this structure. Again, this one is ortho, it is conjugated directly to our nitro group, and you wouldn't necessarily expect its electronics to be terribly different to those of this proton here, which is also a narrow doublet, so we can see it's all the way down here. But in fact, it is a full, almost a full 1 ppm downfield of that signal. What's making that difference? Well, this is also a pi system overlap, but what's happening here is that this ring is, or this attached ring here, is differently orientated. And you can see this better if we look at a model. So if we look first for the two downfield protons I mentioned, here are the two greens. You can see they're rigid and held in position, and they're being affected by the larger pi system of the ring. If we look by contrast at this proton here, we can see that it is actually orientated to interact with the center of this pi system due to this being perpendicular to the main ring plane. And this therefore has a shielding effect and actually pushes the signal quite significantly upfield. Okay, sometimes things which are far away do couple to one another. We've given you as an approximation that you're, for hydrogens, looking at 2 and 3 bond relationships really. Now, you're already familiar with the idea that there are exceptions to that rule. Aromatics, we usually see metacouplings if they're present. Sometimes we even see paracouplings. Those are 4 and 5 bond couplings respectively. Now, this is to do with how good the overlap between the bonds in between are, to allow those spins to influence one another. And so you tend to observe longer range couplings in rigid systems that have good overlap. And in particular, there are specific geometries that accommodate this. And the most important is the W coupling. And you can see a metacoupling as being an example of this, in fact. We have 4 bonds, 2, 3, 4, and we have a W shape. And it's a rigid system. And this holds all of these bonds in the correct orientation for the orbital overlap, which allows these 2 spins to influence one another. Now, the same overlap can be seen in allylic systems, and a different U-shaped overlap is sometimes seen in homoallylic systems. This is less common than a W-shaped coupling, but it's still sometimes observed. And even without a conjugated system, if your ring geometry is rigid enough, as in the case of this bicyclic system here, you can see you have a W-shaped geometry, and actually you can see a reasonably sizable coupling between these 2 protons. So, to give you a personal example, this is a thiazolene, which I've made many times, and you would not expect the red and green protons to couple. For the red proton, you would expect what would be a doublet of doublets and may appear as a triplet depending on the exact sizes of the couplings. However, if you build a model of this, you can see that your ring system is actually very rigid. You have this short double bond here. Actually, this holds the geometry between the proton, which is locked in its position, and the methyl group, which can spin around this axis only quite firmly together. And if we go over here, we can actually see, you can see it from the tilt of the protons, it's less obvious in the shape of the ring, but it's a little bit clearer perhaps if you try and look at the bond of the sulfur here. That we have a W-shaped coupling, and in fact the signal that you observe here looks a lot like a triplet of triplets. So those are not something you'll see in every molecule, but seeing some kind of slightly longer range proton-proton coupling, 4 bonds, occasionally 5, is not that rare. is something you will come across. Something that's quite a lot rarer that I just want to raise briefly is the idea of through-space coupling. Now, I know this makes no sense according to everything previously been told about needing bonding interactions in order to transmit the interaction between nuclear spins. Even so, it does occasionally happen. Usually it happens with heteroatoms. The examples I'm aware of involve fluorine. So here is a classic literature example. And these two ring systems are held at a slight angle to one another. That means that the system is rigid and the hydrogen and the fluorine are in relatively close contact. And this means that you can actually get a coupling of these two atoms through space. And if it was mediated by bonding, this would be a 7-bond interaction. But it isn't. You would be able to see it from the fluorine-carbon coupling. And I also have a personal example where I think I observed this. Again, you can see that it's related to some of my other previous work. And here it's possible to see a splitting for the interaction of the fluorine with this hydrogen in this carbon, but not for this carbon here. So I just want to take a moment to show you a real-life example of this longer range coupling. So here is the compound I mentioned, and here are the two relevant signals I want to show you. So this is the proton, and you can see in this case it has identical couplings to these two, and that is the two 9.3 Hertz couplings here. And then it further couples to this methyl group, and that gives rise to a quartet. You can see quite clearly that it has a J value of 1.7. And this is mirrored if you then go and look at that methyl signal in a doublet with the J of 1.7. So this is an example of a long-range coupling. I just want to finish off with some brief mention of quadrupolar coupling. So we have so far assumed that only spin-1/2 nuclei are ever relevant. And basically I want you to keep assuming this for the most part. Thankfully for medicinal chemists, this is almost always true. And the reason for this is that a lot of the isotopes we have to deal with are spin-1/2 inactive or not visible in our under common NMR settings. So oxygen and a major sulfur isotope are inactive. Hydrogen, fluorine, phosphorus, silicon, and the less abundant carbon-13 are all spin-1/2. The likes of the halogens are quadrupolar, but you don't see them. There are, however, a few cases where quadrupolar nuclei do matter. And a major one, possibly the major one, is boron 11. It's about 80% abundant. Actually, boron 10 is also NMR active, but the couplings will be, these will be smaller, so there's less, you're less likely to see them. Now, being spin 3/2 means that instead of +1/2 and -1/2, you have +3/2 +1/2 -1/2 and -3/2 lines, and this gives you a 1-to-1-to-1-to-1 quartet. As it happens, this is taken from a boron hydrogen example, but your carbon coupling will be relevant a lot more often, actually. A typical example of where you'd see it is this phenylboronic acid. We use quite a lot of boronic acids for Suzuki couplings. And actually the effect between splitting a signal 4 ways and broadening it is to make it much smaller. And since carbon-13 is low abundance and the signal to noise is not usually that good anyway, in practice you generally won't see the carbon to which your boron nucleus is attached. And here's just an example of that, where the red is a simulated spectra of phenylboronic acid, and the black is a real spectra, and you can see that there is a carbon signal missing. And this is the one that would be attached to the boron. Okay, so the last example, nitrogen-14, which is very high abundance, and obviously nitrogen's a nucleus we use a lot, is actually spin 1. However, it is not normally visible. Normally we can't see any couplings from it. However, in the case of ammonium salts, it is occasionally possible to see this interaction between hydrogen and nitrogen, and being spin 1, you'll have +1, 0, -1, which will give you a 1 to 1 to 1 triplet. So this is just something to watch for it with ammonium salts, and if you're not prepared for it, it will look very strange indeed. So I just thought I'd point it out. Incidentally, if this signal looks familiar, this is also the origin of that 1 to 1 to 1 triplet in your chloroform solvent peak, which is from deuterium, which is also spin 1. Okay, so coming to the end of this, I just want to take a moment to talk about what the procedure is when you see something odd in your NMR. And this is relevant for the various weird things I'm pointing out to you today, but it's also relevant to rotamers and second order effects that we've talked about in other tutorials. If you don't understand something that's happening in your NMR and you suspect something unusual is going on, I'd suggest the first thing to do is just to try running it in a different solvent and see if what you're observing changes and if you can make any sense of that change. However, if that doesn't clarify the issue, then I would suggest first get your compound absolutely pure, get good data on it. You should bounce what you're seeing off experienced colleagues. You should always check your data against other analytical techniques. So what do you see on TLC? What's the LCMS trace and mass look like? Can your IR spectra tell you anything? Does the MS or even the high resolution MS agree with you having the correct compound? So look for consistency there with your expected structure, or indeed the structure that you're postulating for your unexpected NMR. I think it's important to define exactly what you think is happening, and of course use the literature, compare it to related structures, if necessary even do some measurements from calculation. There is a reasonable amount of quite powerful NMR prediction software out there. And once you have a good idea of what you think is happening, try and work out how to test it. What can you do to your NMR experiment that will tell you if you're correct? I just want to caution about how not to use this information, because it's very tempting when you have lots of bits and pieces of information like this to use it to produce kind of vague explanations for things that don't make sense in your NMR data. And I just want to caution you that these are unusual phenomena, and some previously observed things like second order effects and rotamers are more common. But even so, the most common explanation for an NMR spectra that looks impure is a sample that is in fact impure. So you need to be careful in explaining away problems with your spectra. So I hope that was useful to you, and let me know if you have any questions or any further information.